Hello, I'm David. I'm a PhD student in Marco's group, and I'm going to be talking basically about the sort of theoretical and conceptual background on first principles electron-proton interactions, and the interpolation uh, thereof. And so I will cover both some kind of fundamentals and then some more recent developments. Um, and all of this is implemented in Perturbo. So it's very relevant to everything that will come after. Um, okay. So Um, yeah, like I said, we'll start with the more sort of background kind of standard workflow. So this will be the interpolation of electron-photon interaction. This includes a short-range part and also in insulators, long-range parts, which we'll discuss. And then we'll also talk about some ways to go beyond the standard DFT approximations, including with GW corrections to electronic structure, spin polarized systems and systems with spin orbit coupling and systems with correlated electrons. Okay. So the electron photon coupling is you can think of it as a scattering amplitude between two electronic states from some phonon displacement, but it's the overlap matrix of in two electronic states of the perturbation potential on the from the phonon on the cone jam potential. And this quantity depends, first of all, on two different bands, a phonon mode and an electron and phonon crystal momentum. So it's pretty complicated, and it also varies significantly as a function of bands, phonon mode, and electron and phonon crystal momentum. So this is just looking at as a function of the Q parameter for some choice of bands and K points. Um, and you can see that throughout the Brion zone, these different coupling of these different phonon modes varies pretty significantly, including some um, divergences at Q equals 0. Um, and so if accurately obtaining the coupling is important for all the calculations we want to do, so it's a key step in the workflow. And so the overview of how this workflow works is there's first principles quantities from DFT and DFBT. So the bands and wave functions from DFT and the phonons and perturbation potentials from DFBT. And these are on coarse K and Q grids, like you would do, any kind of DFT calculation. And we also get these maximally localized Wannier functions from Wannier 90, um, which is a local electronic basis. Um, and we cannot do these calculations at the grids dense enough to get, transporter dynamics um, straight from these quantities. So we need to use interpolation methods where we take the coupling on the coarse K and Q grids, interpolate them and store them in real space, and then we can interpolate that back to any K and Q of interest to use for transport dynamics calculations and so on. And so, like I said, to do these transport and dynamics calculations, we need very dense K and Q grids. Um, DFT and DFBT typically operate on, order of magnitude 10 K points in each direction. Um, but you'll see, for example, this is the electron energy resolved contributions to transport and the total mobility for, I think, gallium arsenide. But you can see it takes well over 100 K points, so something like 600 K points to really converge it. Um, and so clearly that's not practical for DFPT. So this really illustrates why interpolation is necessary. Um, and the strategy to interpolate, I think Marco touched on this, but I'll go over it in a bit more detail, is the real space representation of the electron phonon matrix elements. So Um, we are most used to thinking about electron-phonon coupling in reciprocal space, where it's a coupling of a phonon mode between two electronic bands, each with well-defined crystal momentum. But this can be Fourier transformed into real space. And here it's a coupling where all the quantities are localized. So the electrons are two different Wannier orbitals, or it can also be atomic orbitals on two different sites, um, some distance apart. Um, and the phonon mode is the movement of a single atom in a certain direction. And so that's also localized because it's a single atom. And these are then defined by, you know, um, the index of the orbitals, um, the atom, and the distances between the two or the three different sites. Um, and the good thing about this real space representation is, for the most part, it's short ranged. And there are sometimes long range parts, but those can be handled analytically. So there's, so the key part here is handling the short range part, and that part will decay quickly in these distances between the Wannier orbitals and from the Wannier orbitals to the atom that's moving. Um, and so to get this real space representation, um, uh, actually, I'll take a step back. So um, you can see here in two different real space representations, atomic orbitals and Wannier functions, that um, the the g are kind of decay exponentially as a function of distance between Wannier orbitals, because the Wannier orbitals are localized, and it's actually a little bit more localized for atomic orbitals, but there's a trade-off because you often would need a few more atomic orbitals to represent the same number of bands as Wannier functions. Um, and so this, whichever basis you're working in, um, you can go between K and Q with um, Fourier transforms and inverse Fourier transforms. And so once the coupling is stored on this coarse real space grid, it can be efficiently interpolated to any K and Q of interest. And this method was first developed by Feliciano Giustino, Martin Cohen, and Steve Louie in 2007. And then for atomic orbitals, it was developed in the Bernardi group. And there's several good review articles on Wannier functions and the computational methods associated with that that have been published. So here, this is just one of them. Okay. So here's an example of what the interpolation looks like for a particular, valence band and optical phonon mode in silicon. You can see that this is a plot of the coupling um, at different coarse Q grids with atomic orbitals and Wannier functions. And you can see that whether you use atomic orbitals or Wannier functions, and whether you use even for fairly, coarse grids, the result is very accurate. Um, there's this, the main discrepancy is at this K to gamma point, and that's due to um, longer range contributions to electron phonon interactions. And you see that the treatment of um, the whole coupling, but especially at this point where there's longer range interactions, does improve um, as you include more coarse K points, because that effectively means you have longer range real space grids. Um, and we'll talk more about how to more efficient methods to treat um, the longer range interactions. But the takeaway here is that even with fairly, sparse coarse grids, you can accurately interpolate the electron phonon interaction. Okay, so now I'll go into the treatment of the long range part. So um, in insulators in particular, the electron phonon interaction is not fully short ranged, But the long range parts have sort of simpler analytic forms that can be taken advantage of. So the oftentimes the bigger contribution will be this Froelich interaction, which is a dipole interaction formed by atomic displacements. So this would be the case where basically you could envision this as all the negative ions are displaced in one direction, all the positive in the other. So I think actually these arrows should be flipped. But yeah, this will create a dipole field. And in for longitudinal optical phonon modes with long wavelengths, so Q close to zero. And so in 3 dimensions, the coupling from these modes will go with one over Q. So it diverges, and then in 2D, I don't think it diverges, but it's still strong, and there's still a long range contribution. Um, so yeah, and so this strategy that I'll present on the next slide was initially developed for 3 and 2D by these people. And then there's also a quadrupole term, which contributes a constant long range term to the coupling due to a quadrupole moment of the phonon mode. And some of the early work was done in this group to treat this. And you'll see if you don't treat this, your coupling is off by a constant. Did I? Okay. Yeah. And so the strategy for for both of the long range parts, but in this case for the Froelich part, is to separate out the short and long range parts of the coupling. The short range part can be treated by, Wannier Fourier interpolation. And the long range part, because it's long ranged in real space, it's going to be difficult to treat in real space, but it can be efficiently treated in Q space. And so you can use this analytic sum over Q with these uh, dielectric constants and these Born effective charges, and that will give you the um, contribution from a certain atomic displacement to the coupling in K and Q space. And then you add back the short range part from Fourier interpolation and the long range part from the analytical treatment. And so just an example of this in gallium arsenide and molybdenum sulfide. You can see both of these have long range or longitudinal optical polar phonon modes that diverge at Q going to gamma. And um, the treatment of the long range part essentially captures this very well. So, and it also captures the other Q points well because it has the short range part as well. And then for the quadrupole part, so here you have the coupling going to some constant factor as Q goes to zero. And so you can see that if you don't include it, your coupling is off by some constant factor near gamma. So away from gamma, the coupling appears, the short range part, accurately treats it, and then it goes to some wrong value at gamma. And in piezoelectric materials, this is important for all phonon modes, and in nonpolar materials, this is also important for optical modes. And the way to capture this is with I think with the quadrupole moments of the phonons, and Perturbo can capture this with methods implemented by Jinsu and Batzel in previous years. Okay, so now I'll talk about some first principles methods beyond kind of normal DFT. So the first is using a GW correction for the band structure. So this is pretty simple, but oftentimes DFT will get the band structure wrong. It's kind of well known to underestimate band gaps. And then for for example, this Dirac semi-metal, it also significantly underestimates the dispersion. And getting masses and dispersions wrong is a big problem for transport because it affects the density of states and the band velocities and things like that that are essential to getting the right transport properties. And so the solution here is to assume is basically just to correct the eigen vectors in DFT with those from GW. It's generally uh, been seen, in most cases that the Vannier orbitals don't change very much between GW and DFT, so keeping those is a pretty good approximation. But correcting the eigen vectors for the bands leads to a more accurate band structure and corrects a lot of these uh, properties. And then in the case of spin polarized systems, so this would be the LSDA approximation in DFT, you essentially have two decoupled spin up and spin down subspaces. Um, and so there will be a coupling for each of them, um, associated with the cone jam potential felt by a certain spin and the wave functions for a certain spin. And so it almost performs like two copies of the same workflow. This is an example for iron, right? You have the red spin up and the blue spin down subsystem. Um, yeah, and so that's implemented in Perturbo to treat spin polarized systems. And then um, in the somewhat more complicated case of spin orbit coupling, this would use in DFT, it would use the non-collinear spin orbit coupling with relativistic pseudo potentials, and you use that to do the DFT and DFPT calculations. And then your coupling, basically each band turns into a two-component spinner, as well as the change of the cone sham potential also becomes, gets a factor of two in each dimension associated with the spinners. Um, and it's important to treat that spinner SU2 symmetry properly, as Marco mentioned. And yeah, so when you do these things, you can accurately compute and interpolate electron-photon interactions with spin orbit coupling, and that's used in um, spin flip or spin transport calculations, things like that. And that's also in Perturbo. Where is it? Okay. Um, and then another case where density functional theory can fail is in the treatment of correlated materials. And so a number of complicated things can happen when you have electronic correlation, including, sort of well-known phenomena like superconductivity or multiferroicity, um, and metal insulator transitions. And uh, a number of assumptions of DFT can be problematic, but one of the simplest ones that can go pretty dramatically wrong is that DFT has a self-interaction error, meaning that it doesn't really know about orbitals and it thinks electrons in orbitals are interacting with themselves. And so this can be corrected in the DFT plus U framework by replacing the local part of the cone sham potential with a Hubbard U interaction. And so one case where this works is for the material cobalt oxide. So experimentally, it's an antiferromagnetic mod insulator. DFT gets it wrong. In fact, it thinks it's a metal. I guess this is the density of states. You can see there's density of states at the Fermi energy, which means it's a metal. And DFT plus U predicts it basically right and thinks that it's an antiferromagnetic mod insulator. And then because the DFT is getting the electronic structure so wrong, it's sort of unsurprising. It also gets the phonon dispersion wrong. It predicts it to be unstable, whereas df-pt plus u, so with the Hubbard correction, predicts it to be stable. Um, and so, if you're trying to compute the electron phonon coupling, you need to do this from the starting point of realistic bands and phonons. So we've developed a method to correct the coupling or to use Hubbard corrected density functional perturbation theory for the coupling. And here it looks kind of basically just like um, the the previous coupling that we've seen, but instead of just having a perturbation to the Hubbard or just having a perturbation to the cone-sham part of the potential, there's also a perturbation to the Hubbard part, which is the local Hamiltonian between the 3D orbitals in this case. And the Hubbard U value can be determined ab initio with like a linear response approach or uh, different some other approaches as well. But using this method allows to correct this self-interaction error and get a reasonable coupling for these materials in Hubbard corrected density functional perturbation theory. So to look at this, it's a pretty striking difference if you compare the electron phonon coupling with without the Hubbard U correction to the one with. So if without the Hubbard U correction, first of all, you have these unstable phonons, which produce these kind of weird divergences. But what you don't see is the Froelich coupling because GFT thinks it's a metal, so there's no long range contribution. The Hubbard correction, fixes both of these things, so you get the Froelich coupling for the LO phonons. It's now stable. Yeah, and this is okay. Well, this has now been released as of about a year ago. So, yeah, you can use these corrections for certain mod insulators. Now that I'll note that like this the physics of Hubbard corrected density functional perturbation theory and or just Hubbard corrected DFT in general is it corrects one aspect of the correlation, namely like the self-interaction error. And so it won't work in all cases for mod insulators, particularly if you don't have some kind of other symmetry breaking like antiferromagnetism. But when you do in this case, like this material is antiferromagnetic, also the Coop rate that Marco showed, when you have like an antiferromagnetic ground state, the Hubbard corrected density functional theory and perturbation theory usually kind of produce nice corrections and work well. Okay. And so to summarize this part of the presentation, I've shown methods to compute the methods that are implemented in Perturbo to compute the electron phonon interactions from first principles and to accurately interpolate them, both the short and long range parts. And then I've also shown some, beyond normal DFT extensions, such as correcting the electronic structure with GW, treating spin polarized or spin orbit coupled systems and correlated systems. And so this, in totality creates a good, toolkit to apply to different ranges of materials and do a comprehensive analysis of the electron phonon interactions. Okay, so then in the last part, I'm going to talk a little bit about how the kind of the theory and concepts I presented actually are reflected in a realistic quantum espresso and Perturbo calculation. So I'm not going to talk about the sort of transport and dynamics and stuff in Perturbo. That will be covered in the subsequent talks. But I'll talk about getting the electron phonon coupling and using the part of Perturbo to take the quantum espresso outputs and get the real space coupling. And so to do that, you use these set of tools within quantum espresso. And I'll say that in order to get the right physics and have everything be converged, it's important to do the relevant studies of the lattice parameters, the functional pseudopotentials, what grids you need to converge things, um, how many bands and what projections and stuff you need to Vonnierize if you're using spin orbit coupling or Hubbard U, right? You make all these decisions, and then the key calculations in the workflow are the quantum espresso self-consistent field, which gives you this electron density in the dot temp folder, and then that is used for the phonon calculation, which gives you the dynamical matrix and the dVSEF, or the perturbation potentials, and also to the non-self-consistent field, which gives you the wave functions, which are used to Vonnierize and create the projections to the Vonnier orbitals. And then the phonon and NSCF and Vonnier outputs are used to create this very important file, the epr.h5 file with qe2pert. And this file basically contains the real space G, so G of the electron and phonon coordinates that we discussed. And then that can be used to calculate, further quantities in Perturbo. And so I'll say that there are some, codes and things like this, like relax and matdyne and things like that, that are not directly used here, but it is important when you're doing your own calculations to look into these things to make sure everything is physically correct. Okay. And then I'll give some tips for DFT calculations. So there are a number of parameters that you should look into and converge, but some of the most important are the K-grid and SCF and the energy cutoff. And these things should converge the lattice parameter and the phonon energy, and make sure the bands are correct. For the NSCF K-grid, it doesn't have to be the same as the SCF, and this should be chosen to converge the Vonnierization and the interpolation of the electron quantities. So both the interpolation of bands and the interpolation of the electronic part of the electron phonon coupling are going to depend on how dense the NSCF K-grid is, because that determines how long range interactions you have in real space. And so that's what you should be looking into to converge that. The K-grid, and this goes for all kind of Prion zone grids, is going to scale inversely with the lattice parameter. So for a small material, you're often going to need something in the 10 to 20 range. For a larger material, it's going to be kind of proportionately less in each dimension. And oftentimes you want to choose a K-grid that contains high symmetry K points. So for example, if you're something with like a threefold rotational symmetry that has a high symmetry point, at K equals 1/3, it's better to choose something that is a multiple of 3. You want to use Ibrov to treat the symmetries where possible, just because it increases the chances that quantum espresso will figure everything out correctly. And it's good to check the band structure with, for example, the bands calculation in quantum espresso. And then for the DFPT, the Q-grid should be chosen to converge the interpolated phonon dispersion and electron phonon coupling, so similar to the K-grid. And I'll say that the calculation time is more sensitive to the Q-grid. For most calculations, it depends a bit, but usually it's more sensitive to the Q-grid than to the K-grid. And so you don't want to use an excessively dense Q-grid if you don't need it. If the calculation of the DFPT within phonon.x in quantum espresso is not converging for each phonon that it's calculating, the first two things to try would be to decrease the mixing parameter. I think it's 0.7 by default, and you can decrease it a bit. And increasing the number of steps that are mixed. So it's 4 by default, and you can increase it to something like 8 to 20. And then it's helpful to use these post-processing tools in Quantum Espresso to check that the phonon dispersion is correct. Um, and you can visualize the phonons with this interactive visualizer, which also lets you see kind of what the phonons look like, which is nice. Um, and then Vanirization is probably the most finicky, I guess, for lack of a better word, part of the workflow. And so there's some both art and science that goes into this. And one thing that you want to do is choose the projections wisely. So um, including more Wannier orbitals will generally lead to a better fit of the bands and also will localize the orbitals better. But the downside is the calculations, for example, the interpolation of electron photon matrix elements will scale with the number of Wannier functions squared. So you don't want to use too many more Wannier orbitals than you need if it's uh, a computationally demanding calculation. And then it's important to set the disentanglement windows well. So usually there's two windows, an outer and inner window. In the tutorials, these will be set for you, but when you're doing your own calculations, I would say generally want to set the outer window to include all bands that have significant character from the orbitals that you're projecting onto. And you usually want to set the frozen window to only have the bands that you really want to fit closely. Um, and so oftentimes if your Vannierization looks kind of bad, it often comes from either essentially forcing the calculation to include a band that you don't want, so putting a band that you don't want in the inner window, or excluding part of a band that you do want, so putting a band that you do want outside the outer window. And then it's good to explicitly exclude bands that are completely outside the outer window. And it's also good to look at the output in the wout file and check that the centers are where you expect them to be and the spreads are reasonable. And if the spreads are kind of going crazy or the centers are moving all over the place, that's a case where you should exercise caution. Um, and then some continued tips for how to actually choose the window. I would say there's 3 strategies in increasing complexity for depending on how tricky your system is. So one that works for simpler cases where the bands are mostly the bands that you're trying to Vonnierize are pretty well separated from the other bands would be to plot bands and color them by a different number and kind of visually inspect. And usually you can see, okay, I want to Vonnierize this band, and maybe there's a crossing here, but you can kind of still see it's the same band. And so you're going to include, you know, um, based on the band that you can see. Um, in some cases, though, you have a case like this. So this is some cuprate, I think. And we're trying to Vonnierize this one band at the Fermi surface, and at the bottom it uh, mixes with a lot of oxygen orbitals, and it's less clear which band is we want to include. So 2 strategies here are to calculate the projected density of states. It's a function of energy and see, okay, the d orbital character goes over a certain energy window, or to do what's called a fat bands plot, which is shown here. And that's to do a projected density of states for each k point and use that to see which bands have the associated orbital character of this orbital that I'm thinking about. So, this first trick is the easiest and it will probably work if the bands are well isolated. 3 is the hardest, and this is something that's good to do if the bands are significantly entangled and it's confusing. And then for the electron phonon interpolation, it can help, in general, the interpolation will converge more if you use a denser coarse K and Q grid, because that will lead to longer real space uh, vectors. But it's also important to use good quality Wannier functions. So in general, if they're more localized and if they have kind of a more physical symmetry, um, then you'll often get a better interpolation. And so using the tips on the previous slides is helpful. I think this is the last slide. Yeah. Okay. So uh, yeah, I'm happy to take questions about any of this or from the yeah.